For today's lesson, we're going to be talking about 9.4, which is arithmetic series. This goes off of our previous arithmetic sequences, and a series is really just going to be a summation or the adding of all components of the sequence. So a series is the sum of the terms of a sequence. And we have two ways of writing this. If it's a arithmetic or arithmetic series, we have the sum of the series numbers of terms is equal to the number of terms divided by 2 times the first and the last term. But we can shorten this writing, and we can just use these Greek alphabets. And this is sigma of a of n, sub n. And so we're going to explain that in just a bit, but again, sigma means sum of all terms. So in this one, a finite series is a terminating series, so it terminates with the first and last term. For example, we can see right here, we can have 1, 2, 3, and 4 added together. That is a finite series, and that's going to equal 10. An infinite series is a series that continues without end or without terminating. Same kind of idea, just doesn't end. Now, an arithmetic series is a series whose terms form an arithmetic sequence. And so this is our key thing today. We're not going to be looking at geometric series or anything like that, or geometric sequences, only arithmetic. For anything that's not arithmetic, we're going to have to do it by brute force, and that's just a part of the game. So I'm going to write this formula out two different ways. The sum of S sub n of finite arithmetic series is a sub 1 plus a sub 2 plus a sub 3 all the way to the last term, a sub n. Notice that we said finite. And that's this S sub n is equal to n over 2 times a sub 1 plus a sub n. But if I'm translating this, this means the sum of the finite sequence or arithmetic series is the number of terms divided by 2 times the first term in the series or sequence plus the last term. So this is the way that I remember it. If you need to, go back 30 seconds and rewatch that. We're going to be using this formula for only arithmetic sequences and series. Well, I should say series, not sequences. So on some of our problems, like on example 1, we're going to have to figure out the number of terms that are actually in the arithmetic series. So we have this series, it's 2, then 4, then 6, then 8, all the way to 100. Now you can figure this out pretty quickly with brute force. However, I don't want to do that. So I'm going to set this up in a two-step process. On the first one, I'm going to find the number of terms. On the second one, I'm going to find the sum of all terms in the series. So for the first one, I have a first term, so I have a sub 1, and I have an a sub n, last term. So a sub 1 is 2, my last term is 100. So I'm going to set up this formula to look like a sub n is equal to the explicit formula of a plus n minus 1 times d. Now if you remember, this is the explicit formula for an arithmetic sequence, and this will give me my last term. My last term is 100. My first term is 2 plus the number of terms, which I don't know, times the common difference, which we can just spot from up here. It's 2, 2, 2. So this is an arithmetic series. And so now I'm just going to do some algebra. I'm going to minus 2 from both sides. I end up with 98 is equal to, and I'm going to rewrite this as 2n minus 1, 2 times the quantity of n minus 1. I'm going to divide both sides by 2. And I should end up with 49 is equal to n minus 1. Add 1 to both sides. And we can see that n, or the number of terms, is 50. So we have the number of terms being 50, which is great. This time, I need to say that I have 50 terms. So the sum of all 50 terms in this series will be equal to 50, since that's how many terms there are, divided by 2, times the first term plus the last term. So this is going to get you 25 times 102. And the sum of all the terms in this series is going to be 2,550. So we're going to repeat that again with problem B, or I should say example 1B. Again, I'm going to set it up as 2 different stages. I'm going to find the number of terms. And I'm going to find the sum of all terms. The number of terms here is going to be the last term should be equal to the first term plus the number of all terms minus 1 times the common difference. So in the common difference here, I see a plus 12, another plus 12. So my common difference is 12. I'm going to subtract 8 from both sides. 108 is equal to 12 times n minus 1. Divide both sides by 12. 9 is equal to n minus 1. Add 1 to both sides. N is equal to 10. So what this tells me is that I have 10 terms. So when I want to find the sum of all my terms, I need to use 10 of them. So this is 10 divided by 2. The sum of all 10 terms is equal to 10 over 2 times my first plus my last. And this is going to be 5 times 124. 5 times 120 is 600. 5 times 4 is 20, so this is 620. The sum of all 10 terms of this series is 620. We're going to end up having questions that are a little bit more real life, so we need to look at something like this ceremony at Boulder High, setting up chairs in the gym. There's 20 rows of chairs. It's important. The first row has 10 chairs, and the number of chairs will increase by 2 for each successive row. How many chairs are needed? Well, it didn't tell us how many chairs were in row 20. It told us how many chairs were in row 1, and that's going to be 10. I need to know how many are in the last one, so we got to figure that out. To figure that out, it increases by 2 each time, so we have not a sub n anymore. We have a sub 20 is equal to 10 plus 20 minus 1 times 2. So in this case, we have 10 plus 19 times 2, and then we have 10 plus 38, which is going to get you 48. So the 20th row will have 48 chairs. The first row has 10 chairs. So now we need to have the sum of all 20 rows will be equal to half of 20 times 10 plus 48. So in this case, half of 20 is 10. 10 plus 48 is 58. So now the amount of chairs that we have in this ceremony is 580 chairs. So now we're just going to be moving on to summation notation. We're going to be using this Greek letter sigma to indicate a sum, which we were doing with S of n. But this time we get to see the limits. So this is a more compact way of writing it. So we can also change limits to be, instead of starting at 1, we can have them start wherever we want. Now, the limits are the least to greatest value. So this lower portion is my least, and the top is my greatest. So when we talk about infinite series later, we change the summation, we change the upper limit as infinite if it's an infinite series. To find the number of terms, we actually take the lower term, we subtract it from the upper term, and then we add 1. So on these problems that I give you, it's going to be kind of comical because I don't really give you anything besides 1 to a certain number, so you just count out that. The explicit form of the nth term of sigma notation is the linear function of n. So this right here, we can only really use our formula of summations if it's arithmetic right now. And that's just a part of the game that we're playing. And I want you guys to recognize that it's pretty easy to spot whether or not something is going to be arithmetic or not. So the first one here that I'm highlighting, and I'll change my highlighting color to pink, that is not an arithmetic sequence because what we're doing is we're squaring and then we're adding. If you remember, an arithmetic sequence goes up by the same amount each time. The second one, which is highlighted in blue, is an arithmetic sequence, and we can actually substitute our formulas in. So we'll talk about it down here in our summation examples. On the first one and the third one, I'm going to highlight them in blue. These are arithmetic sequences. The highlight in purple or pink is not arithmetic sequences. So problems 2 and 4 are not arithmetic. That means we'll have to use some brute force, and that's okay because we don't have a lot of numbers that we're dealing with. But we can tell on our number 1 example that it's arithmetic because it's 5n plus 3. This is a linear formula. It's going to go up by the same amount each time, which means that it is an arithmetic sequence. So on this one, what I want us to do is find a sub 1 and find a sub 70 because I have to worry about my first and my last terms. From there, that's all we'll need to do because we'll be able to use our summation formula. So in this one here, this is going to be equal to s of 70, which is going to be 70 over 2, and then we just need to know our first and our last terms. So our first term here, we just plug in 1. So this is 5 times 1 plus 3. That's going to get us 8. Okay, that goes here. And then our last term is 70, so it's 5 times 70 plus 3, which is 350 plus 3 is 353. From here, we're just going to work this out. This is 35 times 363. Let me get out my handy calculator. So 35 times 363. Oops, I'm sorry, it's not 363, it's 361. My apologies. 35 times 361 will be 12,635. So the summation, when we have a linear form, is really easy. We can just use our summation formula that we were doing before. So I'll highlight that. Now, number 3 is also the same thing, so let's do that real quick. On this here, we can see that we have a summation of 3n minus 8. This is linear, so I'm going to use my summation formula that I had before. The summation of all 40 terms will be equal to 40 over 2 times our first term plus our last term. Our first term is 3 times 1 minus 8. That's going to get us negative 5. And then our 40th term is 3 times 40 minus 8. And that's going to be 120 minus 8, which is 112. So this is negative 5 plus 112. This will be 20 times 107. So 20 times 107. we're going to get 2,140. So, problems 1 and 3 are just using the previous formulas that we had. The difference now on 2 and 4 is that we are not in a linear pattern. Whatever we put in, we have to square it. So we have 5 terms here. When I talk about the summation of all 5 terms, I'm just going to write out my formula 5 times and add them together. So my first term that I use is 1 minus 1 squared plus 2 minus 1 squared plus 3 minus 1 squared plus 4 minus 1 squared plus 5 minus 1 squared. Now I stop at 5 because my upper limit is 5. I start at 1 because my upper limit is 1. So from here, we're just going to do some brute force math. 1 minus 1 is 0, 0 squared is 0, plus 2 minus 1 is 1, 1 squared is 1, plus 3 minus 1 is 2, 2 squared is 4. You can maybe see the pattern here. 4 minus 1 is 3, 3 squared is 9, 5 minus 1 is 4, 4 squared is 16. So now we're going to add all these up. So the summation of n minus 1 squared from 1 to 5 is going to be 30. We're going to do the same thing for number 4. I'm going to have 1 squared plus 2 squared plus 3 squared plus 4 squared. Again, the reason why I'm using 1 squared is because I start off at 1. The reason why I end at 4 squared is because that's my upper limit. And this is going to look eerily familiar. 1 squared is 1, 4, 9, and 16. And this is also going to equal 30. So for our non-linear or non-arithmetic sequences, we're going to have to use a little bit of brute force. And to be honest, the easiest way to actually do these problems is to use Excel or some other software. Our last problem was like our first, essentially, or our first story problem. So I'm going to skip it for now, and I'm going to say you should be working on your 9.4 practice, which is mostly all linear. So you should be able to use the summation formula. Find each sum of the finite arithmetic sequence. Make sure you're using that. Make sure you're using that formula. S of n is equal to n over 2 times our first term plus our last term. So make sure you find your common difference on the first 3 formulas, and then work it out on the last 6. Alrighty. If you have any questions, please send me an email. I hope you all have a great day.